Okay, good day. This is Professor Grenfell's Math 12 Statistics class, and we are continuing in Chapter 9, Section 1, continuing. And we're going to be looking at example 9-3 on finding a confidence interval for the difference between two means. And so in this example, it says find the 95% confidence interval for the difference between means in example 9-1. So just flipping back to 9-1, record the different things. We had the two age groups, 26 through 35-year-olds, and then 46 through 55-year-olds. And we were talking about the average number of hours of leisure time per week that they spent. So here we had one sample, chi1 bar, 39.6 hours. And well, here, I'll just go through and quickly record all of the given information in 9-1 and report back. Yes, so I have it all recorded now. So we had chi bar for the sample 1 is 39.6, chi bar for sample 2 for population 2 is 35.4. The sample size for both of these demographics was the same, and equals 35. And I didn't really have room to put it in, but here are the two population standard deviations. So we're assuming that we have population standard deviation. All right, so let's go ahead and flip the page. Make sure we're able to come back to that. Now, let's go ahead and get the formula for our confidence interval. Here, I'll set it up the same way. I'll say the margin of error. How do we make that? We find our critical, in this case it's a z value, if we're using the z distribution. And then we have to multiply by the standard deviation for this distribution. So this is the distribution for the difference between the means. And so remember, it's that same expression that occurs for the standard deviation when we're calculating the test statistic. We're calculating that z value. So it is sigma 1 squared over n1 plus sigma 2 squared over n subscript 2. So that's our margin of error. And then the difference between the means. Remember, when we're performing a hypothesis test, I always like to combine those onto the same side. So most of the time we're saying, okay, mu1 equals mu2 for h subscript 0. And instead of doing that, I like to re-express it as mu1 minus mu2 set equal to 0. So that we're just more used to looking at that type of expression. So what this is going to be is the difference, well, let's see, the difference in the population averages is going to be whatever that difference for the sample averages was, plus or minus, and then we're going to throw in the margin of error. So essentially, that is how, that's a kind of a shorthand way of remembering this long formula that they've got, chi1 minus chi2 bars, because these are sample averages, minus our margin of error, which is z subscript alpha halves, times the square root of this stuff. Yeah, it's a mess. And then that is where the difference in the means is going to be bounded. And then on the other side, it's similar sort of thing. It's the difference in the sample means, and then plus our margin of error, which was z subscript alpha halves times the square root of this whole thing, sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so that's our whole formula that we're going to be using. Okay, let's go ahead and flip the page here. So the first thing I like to do is calculate my margin of error. I break this into two pieces. So margin of error is going to be a critical z-value based on alpha times that whole square root business. And we're just going to go ahead and substitute in the values. We have 1.96 for our critical z-value because our alpha was the same as in the previous problem. We were finding the 95% confidence interval, so we're finding that 1.96 corresponding to the 95% confidence interval. And we're plugging in, what is it, 6.3 squared over 35 plus 5.8 squared also over 35. So we had these two different population standard deviations. And this works out as 2.8. We round it to one decimal place. 2.8 hours. That's our margin of error. All right, so we're going to go ahead and I'll just write down what this is. Chi1 bar minus Chi2 bar is 39.6 minus 35.4. Oops. There. And so that's how we get 4.2 is the difference in the sample averages. And then we have to go in and add and then subsequently subtract away our margin of error to get our confidence interval, to get the range that 95% of the time the true difference would be in that range. Okay. So the difference in mu1 minus mu2 is going to be 4.2 plus or minus 2.8. We'll say it like that. And then for the final answer, we'll write it properly as a double inequality. On the one side, we'll do 4.2 plus 2.8, so we get 7.0. On the other side, we'll do 4.2 minus 2.8, so that gives us 1.4. Right? So with 95% confidence, the difference in the, let's call it the younger group's leisure time and the older group's leisure time, since the younger group appears to have more leisure time, we're taking mu1 minus mu2. And that difference is 95% of the time somewhere between 1.4 and 7.0. So that means that this difference is always positive. Okay? This confidence interval does not contain 0 in here. This is 1.4, this is 7, and 0 would be over here, not even on the scale. Okay? So that means that the difference is always positive. Therefore, what? The younger group's leisure time hours is always greater than the older groups. That means what? That means we are going to be making the same decision as in the previous test. If this confidence interval included 0, we would say there is no significant difference. We cannot reject the null hypothesis, right? If 0 is not contained in this confidence interval, then we're saying, okay, look, this is indeed to the right of 0. That is why this is falling underneath that right tail inside the critical region. And so if 0 is not contained in there, we'll be rejecting the null hypothesis. And so that decision that we made is consistent when we perform the hypothesis test and do it in that style versus creating a confidence interval and analyzing its properties. So we see the same results there. And this is going to conclude Chapter 9, Section 1. We're going to begin in our next video lecture, testing the difference between two means of independent samples. This is using the t-test. And then in 9.3, we're going to do a different t-test. So stay tuned. We'll be back shortly.